Okay, hello everyone. We can start now. So let me see. Okay, I hope my audio is fine. Let me know if there is an issue. Okay. So thank you for confirming. So last lecture we were talking about edge detection, and we discussed three different algorithms, and two were based on first order derivative, and then we talked about Mar-Hildreth, which is based on second order derivative. So continuing on that, today we'll talk about Canny edge detector. So if you look at the algorithm of this Canny edge detector, it's almost similar to what we discussed in Mar-Hildreth. There are like a couple of differences, and we will just focus on those differences. Okay, so the first step, like it's similar to the previous one. We just have to perform image smoothing, and in this case, we are using a Gaussian filter. Then instead of taking a second order derivative, which we did in the last algorithm, in this case, again, we will rely on first order derivative. So the blurred image, we will compute derivatives on top of that. And of course, you can perform that like using a single step. Okay. Now, the third step is we need to find the magnitude of the derivatives. And this we also did for the previous algorithm. So the new thing here is orientation of gradient. So far, you know that when you compute a derivative in an image, which is like a two-dimensional function, so you have to compute partial derivative in x direction and then partial derivative in y direction. And the final result is a vector. And then you can compute magnitude using that vector, which we have utilized. But we can also compute the direction of the edge. And we can compute the angle. So we have the tan inverse formula, right? So we haven't used that so far, but in this algorithm, we will see how we can utilize the direction in which the edge is lying. Okay, so I think there are a couple of questions. Some students having trouble entering Zoom. Oh, okay. Yes, ticket variable host to start. Oh, okay. So let me quickly fix that. So you are saying that's office hours? Let's see. Just wait for a few minutes. I will send the link. So by the way, web courses, it's working perfectly fine with me. I don't know what's the issue. Okay, so this is the lecture. Okay, yeah, the previous link seems like for office hours. So that's my bad. Sorry about that. So I just shared the link for the lecture. And we can actually wait for maybe 1 to 2 minutes. So I think we can take any questions like if you have from the previous lecture while we are waiting. And I think we'll have to start again from the top. And so, is there any other student who is waiting, you know?
think the one that contacted me, I think she was able to finally get in. I'm not sure about others though.
Okay, all right. So that's good. Thanks for confirming. And okay, so if it was just one student, that's fine. I think we can continue because the video is being recorded. So whoever that student is, please go watch the video later. All right. So what we were talking about is the steps in this Canny edge detector algorithm. They are almost similar to Mar-Hillrith, which we discussed in the last lecture. And we start with image smoothing, which is fine. Then we compute derivatives. So in this case, it's a first order derivative. Then we compute the magnitude. And so the additional thing or the new thing in this algorithm is the use of orientations. So we'll see how we utilize the orientation of the edge. And then another additional step is the application of non-max suppression. So we will study like what non-max suppression is. So this is pretty interesting. And again, this concept is not just like important for edge detection. You will later find out that this particular concept can be used in like most of the computer vision problems where you're doing detection. So it could be object detection or it could be activity detection. You might need this non-maximum suppression. It's very widely used. So you should know this concept. Then another new concept in this algorithm will be the use of thresholding. I think there was a question in the last lecture, how we can improve the thresholding, right? So in the previous algorithm, we just pick one threshold, maybe by manual inspection or maybe through some statistics, right? But in this case, what we're going to do is it's a little more sophisticated. It's called hysteresis thresholding. So we will talk about this. Okay, so this is the input image. And the first two steps are image smoothing, and then you compute the first order derivative. And as I said, you can either do like these two steps separately, first smooth the image and then compute the derivative, or you can combine both steps at once. And then the idea is you first compute derivative of your filter, which is Gaussian in this case. And here you can see that if you compute the partial derivative, let's say in x direction of the Gaussian, this is something which you will get. So that's your derivative on top of your Gaussian filter. And if you look like from the top, it will look something like this, because you have like a pit here and then you have a peak here. So it's just showing on the top and just showing the intensity. So this intensity is based on like where this surface lies, like corresponding to this bottom here, right? Corresponding to this y-axis, vertical axis. Similarly, you can have the derivative in the different, like maybe if this is x direction, this could be derivative in y direction. So you will get something like this. And if you just plot the magnitude, your filter will look like this. And of course, this is continuous. You'll have to make this discrete. And then you can apply this filter on this image. It's like standard filtering. You put this filter here, like starting from the top left, and put this like in all the possible locations. That will be your like filtering from the first set of filter, which is in x direction. Then again, you use this filter that will give you in y direction, right? So that's the two steps combined together. So this is just showing you the results of what you will get. So that's your input image. If you apply the first filter, which was like your the x derivative using Gaussian, this is the result. Then y derivative Gaussian, this is the result. And you can see here that this is kind of trying to detect, so this is x derivative, right? So this is trying to detect vertical edges. And in this one, it's trying to detect the horizontal edges. So this you have seen earlier as well. And then what you can do is you can just compute the magnitude. Okay, so magnitude will be, you just take square of each pixel value, sum it with the value of corresponding pixel from this image, and then take the square root. And this is the plot. All right, so this is giving you edges in the input image. But again, we haven't used any thresholding, anything like that. This is just the first two steps, where you have the blurred image and the derivatives of the image. Then what you can do is, in this case, as I said, this is a new concept where you use the gradient orientation as well. And orientation, you know, the formula is simple. You have the partial derivative in x direction, partial derivative in y direction. You just compute tan inverse fx over fy. So that will be your angle at each location. So in this case, we are using color to visualize this because there is no like a simple way to do that. And what we are doing here is that, so your angle will be from 0 to 360 degrees, right? So what you can do is you can assign like each color to each angle. And then what you're doing is you are just showing the color on that pixel location. So if it's red, it means that you can see here that the edge is like, if in this direction, you can watch my hand here, then it will be red. So again, you can see the edge here, right? It's the same direction, so close to red. So all the edges in this direction are red. And again, this purple might be this direction. So you can see that all the edges which are like similar to that direction, then they have this color purple. So this visualization, it's pretty nice. It's kind of give you a sense of like the direction of the edges in this image. Now, once you have those orientations for each pixel location, then I think there is a question from Anshuman. Angles are same as Q angles in HSV. No, these angles are your angle of your edge. So you compute partial derivative in x
I
direction and
meant
partial.
I meant the color, like like 0 degrees, like red and so on.
Oh, you mean the color mapping? So again, that's up to you, right? I mean, you can assign any color to any degree. I mean, you can use HSV as well. That's perfectly
Okay, I thought
fine.
there's some standard. Okay, no
No, no,
problem.
no, no. So this is just visualization. I mean, you can pick like any mapping. So I even don't remember like which mapping was used in this case. But I mean, at the end, it doesn't matter, right? Whether you say like this angle is red or this angle is blue. It's just visualization. Okay.
Okay, thank you.
So now once you have the orientations for each pixel location, what you can do is you can use that orientation for non-maximum suppression, right? So now let's try to understand what non-maximum suppression is. Now, and this is like a very general concept. As I said, it's used very widely in computer vision. So what we do is, and forget about edges for time being. So let's say we are at this location, Q, right? And so this location, let's say it has some value or some magnitude, some value which we are storing. Now, what we do is, if we know the orientation for this location, and that orientation which you can get from like the previous slide. So this orientation is in case of edges, this is like the normal to the edge. So if the edge is in this direction, then this perpendicular is like just at 90 degrees to that edge, right? So then we follow this normal direction of the edge, and what we do is we try to find out the neighboring pixels. Okay, so in this case, sometimes what might happen is, if your orientation is not like well aligned with your discrete space. So if this perpendicular arrow is like in this direction, right, just passing through this black spot over here and this black spot over here, then we don't have to worry. We already know the neighbors, right? So this value and this value. But you know, I mean, this is not continuous space. This is a discrete space. So what may what may happen is that it might pass through like somewhere in between of these two pixel locations. Okay, so in that case, what we do is we compute maybe a value at this location based on the values of these two pixels, and it can be like a weighted average, which we I think discussed in the previous lecture, how to compute weighted average. So for example, if this location is just at the center of these two pixel locations, so it will be just like mean or average of these two values. All right, and if this location is closer to this pixel, then we will provide higher weightage to this value and lower weightage to this value, and then that weightage can be determined using like the distance. All right, so that's fine, that's weighted average. And similarly, you can find a value at this location. So any confusion how we find these values? So I think there is a question from Fernando. How do you color a pixel that intersects two edges? Just choose one. How do you color a pixel that intersects two edges? So if it's intersecting two edges, then it will not be an edge, right? So then depending upon like what magnitude you are getting for the derivatives, you will get some angle, but it won't have any meaning. But anyways, mean you will get a very low magnitude for that location. So at later stage, it won't matter. Okay, so color will be based on like what derivative value you get in the x and y direction. So the ratio of that. Okay, good. So I hope this part is clear. Right now we are looking at this pixel location, which is a Q. And then the goal is to determine the neighboring pixels for this location. So in this case, we just discussed how to get the values at location R and location P. Now, once we have done that, then non-maximum suppression is pretty simple. We just look at the magnitude at this location and compare it with magnitude of this location and this location. If the magnitude is greater than both these locations, we preserve this value. We say, okay, this is an edge in case of edge detection, or if it's an object detection, we say, okay, the object is present here. But if the magnitude is smaller than any of these two, then we just ignore it. We say it's not an edge. So we are kind of suppressing this pixel location if it's not maximum. Okay. So whenever a pixel location is non-maximum, we suppress it. That's why the name non-maximum suppression. Okay, so let's try to understand this from edge detection point of view. So in this case, you can see that, let's say this is an edge grayscale image. So this will be the normal. So if we make a discrete visualization of this, we will get something like this. So the edge is corresponding to this blue patch. Let's say the response from your derivative and smoothing operation. And right now we are looking at this location, this pixel location, which is x, y. Okay. Now we have found like the neighboring pixels. This is like x prime, y prime, and again another neighboring pixel, which is x double prime, y double prime. Now what we will do is we will look at the absolute value of the magnitude at xy, and if it is greater than the absolute value of this location and this location, we just keep that magnitude, which is kind of saying that okay, edge is present. But if it's smaller than either of these two, so otherwise the second clause here, then we just put make the magnitude 0. And if you're making the magnitude 0, it means that okay, there wasn't any edge there. We're kind of suppressing it. Okay, so now let's see, like if we try to visualize that on the result which we get on the input image, what we will get. So this is before non-max suppression, and this is the output after non-maximum suppression. So you can see that what's happening here is it's trying to make your edges thin. So these are very thick edges. And if you think about this, thick edges doesn't make any sense, because you're saying that okay, there is an edge. I mean, you can't have continuous edges, right? There should be some sharp boundary, and that's what this NMS is doing. So NMS is shortcut for this abbreviation for non-max suppression, which is widely used. So after this NMS, you can see that you just have like a very thin line here, and this is like just one pixel location. If you look in any direction, if you look in x direction, only one of the pixel will be having very high magnitude. Again, in the y direction, only one of the pixel will have high magnitude. Okay, so that's NMS, and this is kind of new. We have not seen this in any of the previous algorithms. Now, the second concept was hysteresis thresholding, and again, this is very interesting concept. Now, earlier what we have seen is, so whatever magnitude we are getting for these edges, right? So we do some analysis or maybe run some statistics. There were some like suggestions from someone, I don't remember who made that suggestion. So we can, based on some statistics, come up with like a threshold. I think the suggestion was non-local mean. So that was pretty good. But what if we don't want to do any of that? Is there like a better approach? So what we do here is, instead of having just one threshold, we keep two thresholds. Okay, so one is low and the second is high. And what it's trying to do is, for example, we have an edge like this. So this is a very long edge, and we have an edge like this. This is kind of a very short edge. The y-axis over here is the gradient magnitude. Okay, so what this means is, so this is just one edge because it will have some continuity in your image, right? So this pixel here, the magnitude is pretty high, which means it's saying it's an edge with a very high confidence as compared to this location. All right, so the y-axis is magnitude and x-axis is just like your image dimension, maybe your image space. So what we do is, we have two thresholds. One is called high and the second is called low. Now what we do is, if any pixel location has a magnitude which is smaller than low, we just ignore it. We say it's not an edge. Okay, so that's simple. That's what we have been doing so far. But the next step is, we look at the higher threshold. And again, what we do is, if any pixel location has a magnitude greater than high, we say it's an edge. So all these pixels here for this particular edge, we'll still call them an edge, and these edges as well, right? This edge as well. So it's an edge. So now the interesting thing is, like in this middle area, what's going to happen? Now what we do is, in the middle area, we look at the pixel location and we find that, okay, the magnitude is not like lower than low, and it's also not higher than high. It's somewhere in the middle ground. Then what we do is, we try to figure out if this pixel is connected to any other pixel in form of an edge, which is lying above this high threshold. If that is the case, then we will say it's an edge. Otherwise, we will say it's not an edge. So let's look at these two examples. So in this case, if we look at like any pixel in this edge, and so the rest are like all the connected pixels, but none of those pixels is lying above high. All of them are like below low. So then what we'll do is, we'll say none of these are edges. We'll simply ignore this. And in this case, what will happen is, if we look at this one, although like the magnitude of this pixel is pretty low, it's very close to low, but then we look at the pixels which are connected to this. So these pixels, right, because this is like one single edge, then we say that, okay, they are above high. Then we say, okay, it must be an edge. We should not ignore it. So the idea here is, if you have a very long edge, then some part of that edge might have very high magnitude, and some part of it might be like have very low magnitude. So we discount that portion and we just make the whole thing an edge. Okay, so that's the high level idea. So that's called hysteresis thresholding. And
Professor?
Yes, go ahead.
How do we measure the connectivity thing? Like a portion in the middle area is connected, putting it in the function, or do we learn how do we do that?
So connected components mean it's an algorithm. We are not going to discuss that, but I have a slide later on where I will discuss like how to find the connectivity. And the basic idea is, you just look at the neighborhood, and if let's say, okay, I will come to that slide. I think it will be better there. And if your question is not answered, then we can come back to that.
Thank you.
So I think there's another question from Amelia. What if you have a long edge with some pixels over high and some pixels under low? So all the pixels which are under low, you just say it's not an edge. You will simply ignore it. So that's a very good question. So then you will have to break that edge into two. So for example, in this case, if your low threshold were somewhere like around this level, right, then you will have to ignore all these pixels. So that's not an edge. Okay, so that's a good question. So okay, so if it's above high, you declare edge pixel. If it's below low, non-edge pixel. If it's between high and low, you look for the connectivity. So you'll have to do that iteratively. And if it's edge pixel, if it's connected to like a pixel which has high magnitude. Okay, so now let's talk about, I think it's the next slide. Let's talk about how we find this connectedness. So in this case, I'm just showing you a patch, but you can easily generalize it to like a bigger image. So let's say we are talking about this pixel location. So this is called a 4 connectivity. And in this connectivity, what I will do is I will check like whether the pixel next to this one, right, has a high magnitude or not, whether this is an edge or not. And then I will check this is an edge or not, this is an edge or not. Okay, so if any of these is edges, I will connect this pixel to the next one. So all of this will be like one big edge. So this is called a 4 connectivity. And then you can have 8 connectedness. In this case, we not only look at like the neighboring pixels, we look at the diagonal pixels as well. So if these two are connected, then we say, okay, there is a connection. And then what you will do is, so this is a very small patch, that's your local window, but then you are actually, so you must be familiar, you have studied algorithms, right, data structures. So what you do is, this is kind of a depth, when you can use any algorithm, depth first search, or maybe the breadth first search, BFS or DFS. So when you are searching for this pixel, all the neighboring pixels, you can put them into a stack or maybe a queue. And then you will have to iteratively go through all those pixels again for looking, for finding the connectivity. So for example, in this case, you will go for this pixel and find all the neighbors of this pixel. All right, again for this one. And then whatever pixels you found, that those will be neighbors or connected to this pixel via an edge. So you do that recursively until you find all the connected edges. And this is like another 6 connected, and you can have like in the different direction as well, this direction. So that will be called 6 connectedness. So Momul, did that answer your question? How to find connected pixels?
Yes, it did. Thank you.
Okay, great. Okay, so that was connected component. And once you have that, then you know all the steps, you get the image, and these are the results. You can see that this is much better than what we have seen using the other algorithms. In fact, like Canny, this is still used, and this was, I think, decades old algorithm, but still, because this is pretty fast to implement, and it gives you very, very good results. Okay, so, and again, since we are using Gaussian kernel for smoothing, we'll have different results based on what standard deviation we are using for that Gaussian filter, right? So this is the input image. In this case, the edge detection results shown here is using a standard deviation of 1. And if you increase the standard deviation, then you can see that the edges are like not that fine grained. It's kind of giving you a high level edges. So the basic idea is, if you want like a very rough sketch of the scene at a high level, you increase your standard deviation. But if you're looking for very, very fine edges with all the details, then you use a very small standard deviation. So in this case, you can see that all the edges in this, maybe the wall here, over here, they are detected, right? But in this case, they are completely missing. Okay, so the choice of sigma, it will depend upon like what exactly do you want from that algorithm. So if it's large scale scales, you will have to use a large sigma. And if it's fine features, then you will have to use a very small sigma. So these are like classical algorithms, and we have a long list of this. We can't cover all of those. These are like the most important ones. And later in the course, if we have time, again, we are not sure, but we'll try to touch upon this, how we can do edge detection using deep learning. But I do want to show you the performance curve. So the green dot I showed you earlier was human level performance, right? And all the dashed lines here, these are classical algorithms, and all the solid lines starting from this green one, right? These are deep networks. So you can see that it started in 2015, I think, with a deep edge, this green one, and then it's close to the human level, and that was 2017. And I found like a recent one. So this is, I think, 2019, not very recent, and it's like almost surpassing the human level performance. Okay. So I think this was a question in the last lecture someone was asking. So we have like, and again, this is like one data set. So we cannot generalize it to like the general problem of edge detection. We can say that, okay, in this particular data set, the performance is better than human level. Okay, so that was all about edge detection, and we will continue to neural networks. That is really, really interesting. So we are shifting gears. Now we will talk about neural networks, then we will talk about CNNs. And the reason is after edge detection, we are going to cover feature extraction, and I want to cover like both classical algorithms as well as deep learning algorithms side by side, so that you can compare like how they differ from each other, how the performance differ, how the algorithms are like entirely different. So any questions so far we have for edge detection? We can take those before starting.
Hi, sir. Just a general question. How is generally Gaussian distribution related to images? Now, suppose for data sets, we can say that the distribution of the data set follows Gaussian, but for images, how can we relate it to Gaussian?
Why do you want to relate images to Gaussian?
This, I think we are using like Gaussian filters, right?
Right. We are using Gaussian filters, but probably I didn't get your question, because image is something different, right? Although, I mean, it will have some distribution, but it's a high dimensional space, right? And so if you're asking, so I mean, at a very high level, like if you represent your images like as a distribution, which in fact it is, but it's like in a very high dimensional space. For example, if your image is 600 cross 600, so that's like 36,000, right, million or something, 36 million dimensional space. So in that space, I think if you try to create a distribution, that could be like close to Gaussian.
Okay.
Right, if that's what you mean.
I think someone in the chat said it's related to the noise. So you mean that in images there will be some noise, and this noise follows Gaussian distribution? Is that correct?
Right.
Sometimes?
So noise, right? Noise is random, and it will not follow Gaussian distribution, but it will be. You can approximate that using Gaussian distribution.
Yeah. Okay.
Because noise is random, right? And we assume that it will have some distribution. Okay. And the closest we can have is Gaussian.
Yeah. Thank you.
Okay. Okay. So I think there are a couple of questions. A question from Fernando: if you had to use edge detection in a real project, which one will you choose and why? So probably I will recommend like Canny, because it's efficient, it gives you good results, and it's very robust. Okay, and you can actually vary the filtering, the standard deviation in a Gaussian to like suit to whatever you want to do. Okay, so that's Canny. And if you want to be like more sophisticated, of course, like deep learning approaches, but they will be, I think, again, it depends, like they might be efficient, might not be as efficient as Canny, because for computing derivatives and all, it's pretty fast, right? So I hope that answered your question. And Anshuman, I think that's a comment. It's for noise in the image and not to relate. Okay. So question from Momal: is scanning good at occluded edges detection too? So first of all, this is like a classical algorithm, right? I mean, it doesn't care whether there is occlusion or not, because it's totally based on the statistics and finding the derivatives. So there is no learning involved. So even if you have some occlusion, then it will never know that, right? It will just detect edges, whatever you can see in the image. So I don't think that will be, but like deep learning approaches, which are actually which are learning based, there we might expect that if there is some occlusion, then the network knows that, okay, there is an occlusion, and it can try to interpolate the edges. Or even you should not do that, because if you're computing edges, it's based on what you are actually seeing, right? So occlusion is like more important when you're doing classification or detection. But for edges, you don't want to detect edges which you can't see. Okay, so I hope that clarifies it out.
Professor, what is meant by occlusion?
So occlusion is, so for example, you're doing object classification, right? Let's say detecting cars. So then sometime what may happen is, in your images, you are not seeing the whole car. There might be like maybe a pole in front or tree in front of car. So that's called occlusion. And then if your algorithm can still say that it's a car by only seeing partial part of that car, then
Okay.
you can say that it's robust to occlusion.
Okay.
Okay. All right, so now let's start neural networks. And I think next week we are going to have a short tutorial on this, where a couple of things. The first will be, we will provide you access to the GPU cluster we have here at UCF, so that you can run your code for your projects and even for your assignments on that. So that will be one thing. We'll provide